Hello student, so I'm going to ask some questions on atomic structure as per your request. So the question is, the kinetic energy of an electron in the second pole orbit of a hydrogen atom is equal to x squared by x Na naught squared. The value of 10x is, so we have to find out the value of x to find out the value of 10x. In this case, A naught is the pole radius as usual, and we have to round off the answer to the nearest integer. So let's get started. So the kinetic energy of an electron, just don't get scared by this term because we can use the usual equation which we know from our childhood. The usual equation for kinetic energy is half m squared. And from the Bohr's theory, we already know that mvr is equal to mh by 2 pi. That is, the angular momentum is an integral multiple of h by 2 pi. So from this, we will be able to get the value of v, which is mh by 2 pi m r. So we substitute this value of v in the kinetic energy equation to get half m nh by 2 pi m r whole square. We take this down. M square x square by 4 pi square m square r square. Now we cancel one m and we get an equation 1 by 8 m square x square by 4 pi square m r square. Now from Bohr's theory, we already know another equation which is Rn equal to A0 L square by z. In this case, Z is equal to 1 since this is an hydrogen atom. And here we have been asked to find out for the second Bohr orbit. So that means that N is equal to 2 in this case. So Rn is equal to A0 2 square, which is equal to 4, and writing it in one step, by 1, which is 4A0. So Rn is equal to 4A0. We put this value of R into this equation of kinetic energy. So let me rub this part and continue. Kinetic energy is equal to 1 by 8 m square l square by sorry for the 4 so pi square m 4A0 square. 1 by 8, 4 4s are 16 pi square m into 16 A0 square. Now in this case, we have to find out the second Bohr orbit. So n is equal to 2. Since n is equal to 2, the kinetic energy equation that we get is 2 square, which is equal to 4x square by 8 pi square m into 16 A0 square. See, we start from the basic equations and then we arrive at this main equation. So let me knock this part out to continue. The final kinetic energy equation that we take is h square by 32 pi square m A0 square. So this is the final equation that we get obtained. So now, in this case, what did we have to actually find out? Here you can see that we have arrived in this form: x square by ma0 square, x square by ma0 square. Here x square by ma0 square. So what we require is x. This x in this case is x is equal to 32 pi square. We require the answer in the form of 10x. So therefore, 10x is equal to 10 into 32 pi square, which is 320 pi square. Erasing this part. So 10x is equal to 320 pi square. We put the value of pi, which is 3.14, provided in the equation in the question. So we arrive at the 3155.072. This has no units because, as you can see clearly, this is a constant. This part is a constant. This 32 pi square. This is a total constant, so this has 2 units. And if we have to round it off to the nearest integer. So the final answer is 3155, and this is the value of units. So as per your request, there is another question from atomic structure which is presented on the board. Match list 1 with list 2. There are 4 things in list 1 and we have to match them with the options in the list 2. Psi MO is equal to psi A minus psi B. So there is a negative sign between two wave functions, and psi MO is the wave function representing a molecular orbital. So psi MO is equal to psi A minus psi B. Mu is the dipole moment. Mu is Q into R, that is charge into distance between the charges. And the next one is Nb minus Na by 2. Nb is the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital by 2, that is their average. And D is psi MO is equal to psi A plus psi B. So there is a positive sign over here. These two look similar but they are just different in sign. So I will explain the significance of everything. And in list 2 we have to match all these with regards to list 2. So what is the answer? Now first let me explain what psi MO here means. So in this case, when we are having bonding, when bonding is taking place, suppose between two p orbitals. So we can consider this some wave function psi A, wave function psi B. So these two p orbitals, when they are bonding with each other, so they come together to form a very, very big bond. So this is a bond. This is a bonding molecular orbital. This is how we draw that molecular orbital. And so what exactly is happening in this case? Can you understand? So what exactly is happening? Addition of psi A plus psi B is occurring. So I have explained this to you in a very simple way, but this is much more complex. But for the purposes of understanding it easily, I have explained it in such a way. So this here in this we have added psi A and psi B to form psi MO, and due to this psi MO, in fact this D option psi MO, psi A plus psi B, in this case is a bonding molecular orbital. So this we join with this. D is 2. Okay. Now let me erase this part. So now what happens in case of anti-bonding? So again I take the example of two p orbitals. This is just for demonstration purposes. The actual scenario is a lot more complex than this. So if this is negative, this is positive, and this is positive and negative. So what happens? There is an anti-bonding. There is a node in between these two. So there is an anti-bonding. This is called an anti-bonding orbital. So since there is a node in between them, these two orbitals will not overlap. These will not overlap on each other. So this is the anti-bonding. This will not overlap on each other. So what happens during anti-bonding? Negative overlap occurs. So let me write with another color. A negative overlap, that is no overlap occurs, and hence our wave function looks like this: psi A minus psi B, where psi A is this one and psi B is this one. So psi MO is psi A minus psi B. So in this case, what can we join with option A? This is anti-bonding molecular orbital. Now, so I hope it is clear to you. Now, in case of option B, which one will be paired with? So mu is the dipole moment, which is equal to Q into R. If you have read the chapter carefully, you will understand that mu is actually dipole moment, so there is no question. We will directly join this B with 1, and we are left with Nb minus Na by 2, which is the bond order. How? Because Nb is the bonding, the number of electrons in bonding molecular orbital, and Na is number of electrons in antibonding molecular orbital. ABM is antibonding molecular orbital, BM is bonding molecular orbital, and hence bond order is Nb minus Na by 2. So this is connected to option 4. So which one is it corresponding to? A is for 3, A is for 3, B is for 1, B for 1, C for 4, C for 4, D for 2. So D for 2. So option 3 is correct. Option 3. Now another interesting question is the number of radial and angular nodes in 4D orbital are respectively. There are 4 options. So let's first discuss what are radial and angular nodes. What are the formulas required for finding out radial and angular nodes? Total number of nodes. For total number of nodes, the formula is n minus 1. But this has not been asked from us right now. What they are asking is radial and angular nodes. So for radial nodes, the formula is n minus l minus 1, and for angular nodes, it is very simple. It is L. So this is very easy to remember because these are very short formulas which one must remember for solving simple questions on atomic structure. So for 4D, what happens? In case of 4D, for 4D, n is equal to 4, and for D, L is equal to 2. So in case of D, L is equal to 2. So for finding out radial nodes, number of radial nodes n minus l minus 1, 4 minus 2 minus 1, 4 minus 3 is equal to 1. So there is one radial node in 4D, and number of angular nodes is equal to L. In case of D, 4D, the L is 2. So number of angular nodes is 2. So the correct option will be A. Radial is 1 and angular is 2. 1 and 2. This is the correct answer. So the question I'm going to discuss right now, these types of questions don't usually come in the JEE Mains or advanced exams, but these questions help us in increasing or expanding our concept regarding atomic structure. So let's get started. Consider the hypothetical situation where the azimuthal quantum number L takes values 0, 1, 2 to n plus 1, where L is the principal quantum number, then the element with Z, 9, is the first alkali metal, 13 has a half-filled valence suction, 8 is the first noble gas, and 6 has 2p valence suction. So it is important to note that this is a multiple select question. That means there are multiple correct answers. So let's find out what are the correct answers. So in normal cases, the principal quantum number is denoted by n, and the azimuthal quantum number ranges from 0 to n minus 1, and this azimuthal quantum number is denoted by L. So L ranges from 0 to n minus 1 for a particular n value. So for the suction n is equal to 2, the L values will be 0 and 1 in this case, in normal circumstances. But here we have been told that in this case, in the hypothetical situation, L takes the values of 0, 1, 2 to n plus 1. In this case, it was taking the values of 0 to n minus 1, but in the hypothetical state, that is L dash, it takes the values of 0 to n plus 1. So in this case, if in the hypothetical state, if we want to find out the number of azimuthal quantum numbers or the number of subshells, then the subshells will range from 0, 1, 2 and 3, because 2 plus 1 is 3. So we are getting 2 more subshells in this case. So how to solve this question? First drop the board. So in case of atomic number 9, what happens? What is the electronic configuration? 1 is 2, 2 is 2, 2, 3, 5. This is the electronic configuration. So for n is equal to 1, in this case, for this one, we want to find out the number of values the azimuthal quantum number can take. So for n is equal to 1, then L is 0, 1, and n plus 1 means 1 plus 1 is equal to 2. So in this case, let's find out how the subshells look like. This is the S. N is equal to 0 means S, N is equal to 1 means P, and N is equal to 2 means D. So what do we have in the new format? In this format, what do we have? In this format, the electronic configuration, the new electronic configuration that we have is 1s and 1p and 1d. So in the old format, we had 1s, 2s and 2p. In the new format, we have 1s, 1p and 1p. We have 3 types. In the old format, as you know, that L was 0. For n is equal to 1, L can only take the value of 0. So in this case, in n is equal to 1, in n is equal to 1, we get only one subshell, that is n is equal to 0. That is the S subshell. But in the new format, that is the azimuthal quantum number ranging from 0 to n plus 1, we get 3 types of subshells, 1s, 1p and 1d in n is equal to 1 level. So what happens is we get 1p, 1s, 1p and 1d. Yes. Now let us fill up the electrons. 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So you see that only one electron is filling up 1d. So the electronic configuration becomes, the new electronic configuration becomes 1s1, 1s2, 1p6 and 1d1. So my question was 9 is the first alkali metal. Now, so the first alkali metal is lithium. How does it look like? The electronic configuration of lithium is 1s2, 2s1. So, is it similar? No, it is not. Why? Because lithium or alkali metals are typically S block elements. And in this case, this is a D block element. So this is not true. So we cross it this way. This is not true at all. So moving on to the next option, 13 has a half-filled valence shell, subshell. So let us find that. In case of n is equal to 1, we have already found out that the electronic configuration is 1p and 1p. This is how the electronic configuration of n is equal to 1 looks like. So in case of 13, z is equal to 13. How does it look like? 1 is 2, 2 is 2, 3 is 6, 3 is 2, 3 is 1. That's that's how Z is equal to 13 looks like. Okay, so now let us arrange the electrons over here. 1s, 1p, 1d. So 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this statement is true, right? 13 has a half field valence substrate. So this is 1p, 1d. 1d is the valence subshell, which is half filled. Right? So this statement is correct. 2 is correct. So the third statement is 8 is the first noble case. Let us find out. So 1 is 1p, 1d, or n is equal to 1. And 8 is the first noble case. Z is equal to, or Z is equal to 8. How does it look like? 1 is 2, 2 is 2, and 2p, 4. Right? Okay. 1 is 1d. 1d. So how does it look like? 1, 2, 3, 4, 5, 6, 7, 8. So this is beautifully symmetric, and this is forming a noble gas configuration. This is a fully filled orbital. So there is no d orbital, so p orbital, and it is fully filled. So this statement is correct. 8, Z is equal to 8 is the first noble gas as valence shell, valence subshell is fully filled. So now let us prove that whether the fourth option is correct or incorrect. So for Z is equal to 6, what happens? They are saying that 6 has a 2p valence substrate. Let's see if it is true or not. Again, 1 is 1p and 1p. So 1, 2, 3, 4, 5, and 6. 1 is 1p and 1p. But in this case, they have said 6 has a valence subshell which is 2p. But in this case, we have a valence subshell. This is the valence subshell which is 1p. So this statement is incorrect. So fourth option is incorrect. So we have two correct options, that is 2 and 3. Correct options